Welcome to Statistics Learning Session. Today we'll be talking about chi-square test, the main ideas for a chi-square test. We have been discussing about chi-square tests since past few sessions to understand or to create a background for the main ideas for chi-square test. So today we will be discussing the main idea here. We have to compute the Fisher information in multinomial model. Now to do that, we have to create a log likelihood of x with respect to p. Now let's do that. Let's create the log likelihood and let's let it be a L1 of x1 with respect to p, and it's going to be a log of p, an indicator that is x equal to a1, and there will be more terms than that, and it's going to be log of p, pk, and indicator x is equal to ak. Now next step, what we have is we indicate a partial derivative of this expression. Now let me take a partial derivative of this with respect to p1, that is log L1 and x1p with respect to p. Now can you tell me what would be the answer for this? It's going to be an indicator such that x is equal to a1 and it's with respect to pj. That's what it's going to be. Now next thing when you do is when you compute a variance for this guy, and I need to look at the outer product of the gradient times the transpose. So for this, I need to take the one more time with respect. I need to take derivative one more time with respect to pj, and let's do that. That is, it's going to be d square and log L1 xp with respect to pj, and it's going to be a equal to. Can you tell me what's going to be? What's going to be the answer for this? Think about it. It's going to be an indicator again, and it's going to be respect to AJ, and it's going to be respect to PJ. That's what's going to be. Now we need to compute the Fisher information, and Fisher information is a negative expectation of this guy right here. This guy, it's going to be a negative expectation of this guy. That is, expectation P is equal to minus expectation of d square log L1 x p with respect to pj. So this is going to be our Fisher information. Now what we need to do is we need to create this will give us because of this we'll get a matrix. Fisher information here is a matrix, and this matrix will have a off diagonal element will be equal to 0, and diagonal element will be equal to non-zero. That is it's going to be such that IP is going to be such that where these elements will be non-zero and this will be a zero. Now we have to find what are those diagonal elements. The formula for diagonal elements, what we need is we need to understand that for diagonal elements, that is when j is equal to j, it's going to be 1 by pj. And diagonal elements will be non diagonal. These are for diagonal elements, and for non-diagonal elements, it will be a zero. That is, I j k is equal to 0 for j is not equal to k. And how this come to be? This is because what we are saying here is that d square d p1 derivative pj is equal to 0. So whenever we have this, we are taking two derivatives here, right? And these two derivatives, when pj is equal to pk, when pj is equal to pk, then it's going to be a 0. When pj, when j and k are different, then it's going to be a 0. That's what we are saying here. Now we know that this Fisher information is such that it's a diagonal array where off diagonal elements are 0 and diagonal elements are non-zero. Now what we have is, for this Fisher information, what we are doing is that we'll take a look at this slide here, and we know that this is exactly what we have here. That is, this expression, what we have is n p hat p naught Fisher information times p, thus p naught equal to the expression that has been provided in the slide, that is n, the summation of that, and p minus p naught square pj. This is what we have here, and this is exactly what we get. Now the problem is that even this is wrong in a sense that we have a we don't have the full this when we do by pj, what we are saying is that the pj are not independent when we do this, but the in fact is that the pjs are independent, and because of this pj depends upon the pj. That's why we have to be careful when we do this. In general, when we do when we have a zero matrix, then this is not a problem. But if it's in this situation, this will be wrong. That's what we are saying here. Now let me summarize what we learned today. We created we took the log of the L1 and we created some kind of expression here, and we took first derivative, and we took second derivative, and then got we took the expectation of this negative expectation, and that came out to be a Fisher information. And for Fisher information is a comes out to be a matrix where off diagonal elements turn out to be a 0, while diagonal elements is a inverse of 1 by pj. And why off diagonal elements are 0? It is saying that when we have a second derivative, is equal to 0, and that's what saying the second derivative, which is also a part of pj, it is becomes 0. And this was really exactly what we have. Now we multiply this into this expression, and this is exactly what we get in this. This is what we get. And this seems to be wrong in a sense that what we have pj are not dependent, but but we have a pjs are supposed to be independent, and because of this becomes wrong unless we multiply by a zero matrix. So that's all for today. I'll see you next learning session. Thank you so much.